All right, welcome back, everybody. Today we're going to be doing section 6.3, which is all about trigonometric equations and how to solve them. Remember, we're skipping section 6.2. We'll do that after section 7.1, so we'll do it then. But now let's talk about trigonometric equations. All right, so here's the overview. We're just going to talk about solving them, solving trigonometric equations in linear form, in quadratic form, using some identities, and then using a calculator. One thing I'll say is this section is actually a pretty short one. It's not too bad. You can use a lot of the techniques you remember from algebra, and you're gonna need to use the techniques that we talked about in section 6.1 a couple of times. So make sure you've watched that lecture and probably tried that homework as well. Just make sure you're comfortable talking about inverse functions like inverse sine, inverse cosine, and so on. All right, so let's get started. Frankly, this lesson is really just a set of examples. There's no new theory, there's no new definitions. It's really just a set of examples. So let's start with a simple one. Determine whether pi over 4 or pi over 6 is a solution to the equation 2 sine of theta minus 1 equals 0. So I want you to think about this one on your own, and then we'll do it together in just a minute. All right, let's do it together. Well, if those angles, well, let's start with pi over 4. If pi over 4 is a solution, then that means if we take pi over 4 and we substitute it for theta here, then we should get something that's true. So let's try that. Here we go. If we plug in pi over 4, well, what's sine of pi over 4? It's root 2 over 2. So we're going to get 2 times root 2 over 2, which gives us root 2 minus 1, and that is not 0. So root 2 minus 1 is not 0, which means that pi over 4 is not a solution to this equation. However, if you instead plugged in pi over 6, you would get this. Sine of pi over 6 is 1/2. How do you get that? You think about the unit circle. But then 2 times 1/2 is 1, so you get 1 minus 1, which is equal to 0. And so we're good with pi over 6. So pi over 6 is a solution. Pi over 4 is not a solution. So that's how you can check. All right, now let's do this one. Solve the equation cosine theta equals 1/2. Think about this one on your own for a minute, and then we'll do it together. All right, let's work on this one together. Really what we're trying to say is what angle has a cosine value of 1/2? And when I say that out loud, hopefully you said something similar out loud to yourself. That's basically the inverse cosine, right? So we want to know what angle has a cosine of 1/2. And so when we think about the unit circle, okay, cosine is 1/2. That means it's the short leg. So horizontal displacement is the short leg. So we should have this. And we know that the angle pi over 3 is a solution to this, right? So pi over 3 is definitely an answer because cosine of pi over 3 is 1/2. But there's a catch here. And the catch is that we don't need to employ arc cosine to be able to solve this question. And there are actually many solutions to this equation because there are many, many angles that have a cosine of 1/2. There's infinitely many, in fact. So what we just did was we found one solution, but that doesn't mean that that's all the solutions. And we need to account for the periodicity. We need to account for the repetition here. So the domain of cosine is all real numbers, but it's also 2 pi periodic. So we found a solution, well, we found one solution in the interval 0 to 2 pi, but we didn't find even all of them in the interval 0 to 2 pi. So there's actually two. There's two here. And I'll draw the unit circle here again in just a second. But if cosine is 1/2, there are two angles in the first 2 pi radians that are solutions. So let's draw the unit circle here again. Boop. We found this one. This is a cosine of 1/2, right? But there's another angle. So if you go here, that angle works. But then also, if you go all the way around to here. Oop, all the way around to here. You'll get another one. And what's this blue angle? This blue angle is 5 pi over 3. There we go. So there's two solutions just in the interval from 0 to 2 pi. And let's take a look at what a picture of that looks like. So here's the graph of cosine in blue. This is the graph of cosine. And if we plot the line y equals 1/2, we can see that it intersects the graph at these 2 points. Those 2 points correspond to the solutions that we were looking for. So if you map down to the x values, if you map this down to here, you get pi over 3. So that's a solution to the equation. And then if you map down here, you get 5 pi over 3. So just in the first interval from 0 to 2 pi, there are two solutions. But the domain of the cosine function is all real numbers, all real numbers. So we're going to get more than just these two solutions to this equation. So we have to account for that. Yeah, so the way that we do it is this. We know that if you add integer multiples of 2 pi to each of those solutions, you will get another solution because you're essentially just going around the circle again, right? So let me go back to my unit circle picture that I sketched roughly right up here. Let me erase some of this bit for a minute. All right, so we had this solution first, the little arrow there. But another solution to the equation is the angle that goes all the way around and then back. And then another solution is the angle that goes all the way around twice and then back. So if you keep adding integer multiples of 2 pi, you get another solution, and then another solution, and then another solution, right? Same thing for the blue angle. So maybe I can erase a couple of those. Yeah. So the blue angle, we found this solution initially, but there's another one because you can go all the way around again, add 2 pi to that, you get another solution, and you can keep doing that over and over and over. You can also consider negative angles. So you can go backward. You can go this way, and you could go around again. So there's infinitely many solutions. We just have to think about the fact that you get another solution when you add an integer multiple of 2 pi. There we go. And so that's how we get the general solutions. So down here in the box, those are the general solutions. Let me highlight them for just a sec. And let's take a look at this structure before we go to the next example here. So what this says is that for all k in the integers, pi over 3 plus k times 2 pi will be a solution. And 5 pi over 3 plus k times 2 pi will be a solution. A quick notational review here. This symbol here, this fancy z, that means the integers. So that's the set of the integers. And this little symbol, that little e looking thing, that just means in. So it means in, or it means is an element of. But basically we're just saying that whatever k is, it's got to be an integer. So if you take pi over 3 and you add, highlight that, if you take pi over 3 and you add 2 pi, you get another solution. If you take pi over 3 and you add 4 pi, you get another solution. Add 6 pi, you get another solution. Add 8 pi, you get another solution, and another, and another, and another. So there are infinitely many solutions. And so what's in the box here are the general solutions to this equation, the general solutions, just like so. I've got a picture here as well. If you go to Desmos and you try to graph this and graph the line y equals 1/2 also, you'll see that the line y equals 1/2 intersects the graph infinitely many times. It intersects it here and here and here and here. So I basically just did an interval from negative 2 pi to 2 pi, and you can see that there's all these solutions. There's all these solutions. Okay. Let's do another example. This one's a little bit different. So I want you to think about this one. Think about it on your own for just a minute. All right, now try to say something out loud to yourself, just out loud so your brain can get that feedback to see how you would solve it. All right, now let's do it together. So this time we're trying to solve sine of 2 theta equals 1/2. Sine of 2 theta equals 1/2. So if we're trying to solve for theta, we've got to get through that sine first. So really what we're trying to say is, what double angle has a sine of 1/2? That's a little bit funky at first, but maybe instead of thinking about double angles for a minute, we should just think about sine values, right? So sine is vertical displacement. So no matter what angle we're talking about, oops, here we go. No matter what angle we're talking about, we want the vertical displacement to be 1/2. Okay, vertical displacement is 1/2, so that means that it's going to be the short leg, so it's going to be this right here. There we go, that's 1/2. So what angle has a sine of 1/2? This angle is going to be, oh geez, what is it? Pi over 6? Yeah, that's right. This is the smaller one. But there's another one, right? So you can go around the top of the circle. Oops, sorry, go around the top of the circle, and there's another one over here. That's also 1/2. And then you can go around and around again, as we'll see. But there is a little bit of a catch. So let me go to the slides. What we have shown is that 2 theta is pi over 6, or 2 theta is 5 pi over 6. And this is for any 2 theta in the interval 0 to 2 pi. And the important thing to notice here is that the solutions are in terms of 2 theta, not just theta. And that's one of the reasons it's so important to really just make sense of what sine is giving you. Sine is just giving you a vertical displacement. And what we found is we found angles where the vertical displacement was 1/2. So that's why what we really got was sine of this thing is 1/2. And so that means that this thing is going to be pi over 6, or 5 pi over 6. All right? So it's a little bit subtle, but just remember we're trying to find where the vertical displacement is 1/2. And then we'll get to the solution for theta in just a minute. Just like before, you can add integer multiples of 2 pi to each of these, and you'll get another solution because sine is 2 pi periodic. So for all k and z, we actually have these two results. Or maybe I should say these infinitely many results. There we go. So these will give you solutions to sine of 2 theta equals 1/2. But we wanted to solve for theta itself. So now what we have to do is we have to take those results and divide both sides by 2. And we get this. So if we divide both sides of this equation by 2, we get theta is pi over 12 plus k pi. And if we divide both sides of this equation by 2, we get theta is 5 pi over 12 plus k pi. And those are the general solutions. So there's some subtlety there. For one, you need to remember that you're solving for 2 theta when you solve initially. Then you need to remember to add the integer multiples of 2 pi to account for all of the repetitions, the periodicity. Then you can solve for theta and get your final result, pi over 12 plus k pi and 5 pi over 12 plus k pi. All right, so this is a good one to ponder. You'll have some examples in the homework, you'll have many examples in the homework, but just take a minute to think about this one. All right, now let's check out the next example. It's related to this one. So here we're being asked to solve the equation that we had before, but we want to restrict theta to be in the interval 0 to 2 pi. Now, we already found the general solutions in the previous example. So we found that the general solutions are going to have this form, right? But because we are being told that theta is restricted to this interval, that theta has to lie between 0 and 2 pi, all we really need to do is just increment k and collect the solutions that fall within that interval. So when I say increment k, I just mean count. So let k be 0, let k be 1, let k be 2, let k be 3, let k be 4, and see what answers you get, and then see which ones actually lie in the interval 0 to 2 pi. So when you do that, you'll get this. So let me erase some of these highlights for a minute. Let's focus on this for a minute. If I let k be equal to 0, then I get this solution. And pi over 12 is safely in the interval 0 to 2 pi. So that's all good. There we go. Now, let's look at this solution for a minute over here. 13 pi over 12. So this is what you get when you let k be equal to 1 in this solution. If you take pi over 12 and you add pi to it, you're going to get pi over 12 plus 12 over 12 pi, which is 13 over 12 pi, and you get this solution. There we go. All right, now what you'll notice is if you try to add 2 pi to that, you overshoot the interval 0 to 2 pi. So if you try to do pi over 12 plus 2 pi, then you end up with a result that's outside of this interval. You end up with a result that's too big. So that means for this equation, we basically can only increment k twice. K is going to be 0, k is going to be 1, and we get 2 solutions that are in the interval. All right, now go to the next equation and do the same thing. So if we let k be equal to 0, actually, let me erase this too. There we go, erase these. All right, there we go. So if we let k be equal to 0, then once again, we're going to have 5 pi over 12, which is good because that's within the interval 0 to 2 pi. And then if you let k be equal to 1, you'll see that you get 17 pi over 12. And that's the biggest you can go. If you try to add 2 pi, you're going to see that you overshoot the interval 0 to 2 pi, and so that's it. Those are the 4 solutions. Let's take a look at a picture for a minute. So this is a picture of what the graph looks like. So the graph that's here is the graph of sine of 2 theta, right? So sine of 2 theta. And then what we did was we plotted the line y equals 1/2. And what you can see is that in the interval from 0 to 2 pi, which is what's plotted here, come back. There we go. The interval from 0 to 2 pi, that graph it repeats itself twice, right? Because remember, what does this thing do? That changes the period of the function. And because that number is bigger than 1, it shrinks the period of the function. So the graph that we're looking at actually duplicates itself twice within the interval 0 to 2 pi. But if you draw that line, y equals 1/2, you can see where all the solutions are. The solutions are right here, right here, right here, and right here. And there's all those solutions. Then you can, I should say, you should map them down. Look at the x values. This one will be pi over 12. This one right here is going to be 5 pi over 12. This one right here is going to be 13 pi over 12. And then this one right here is going to be 17 pi over 12. Just like that. So that's why you're getting 4 solutions in the interval 0 to 2 pi. All right, moving along. Let's do another example here. Let's solve the equation tangent of theta minus pi over 2 equals 1. And so try to work this one out on your own. Think about it for a minute first. All right, now try to calculate this one on your own. Things to remember is what is tangent, what are you solving for, and remember the periodicity of the function, because we're going to have to consider that. All right, let's do this one together. Oops, sorry, wrong thing there. There we go. Let's do this one together. Okay, so what is this really saying? Again, we're saying we want tangent to be equal to 1. So what angle has a tangent of 1? Pi over 4. We've seen this a few times, right? So here we go. If tangent of theta minus pi over 2 is equal to 1, then that means that theta minus pi over 2 has to be equal to pi over 4. And that's for this in the interval 0 to pi, right? So a couple of things to note before I go forward with this. Remember that the period of tangent is pi. It's not 2 pi, it's just pi. So we can look for solutions in the interval 0 to pi first, and then we can add the repetition term to consider the periodicity. But here, we're going to have to solve this for theta. We're going to have to solve that for theta. But before we can solve that for theta, we need to include those repetitions. So this is what we get next. Let me erase this, and let me highlight this. Here we go. Just like so. So we need to add k pi, because if you add pi, or an integer multiple of pi, you're going to get another solution and another solution and so on. Now we can solve for theta. So we're going to basically add pi over 2 to both sides. And then we get this as the general solution. There we go. That's the general solution. And that's for every integer k. 3 pi over 4 plus k pi plus k pi plus k pi. Okay, so let's talk about solving trig equations that are in linear form. So linear form just means that the equation or the function you're working with is linear in a trigonometric variable. So maybe you can kind of see it here, but if not, that's okay. This structure on this side essentially looks like, well, how do I want to say this? Let me say it like this. Let me say it like this. Erase this. If you consider sine of theta a variable just as itself, then what you have is you have an equation that's essentially the form of a line. The equation is the form of a line. It's essentially mx plus b equals 0. So that's why they call it linear form. Anytime you hear linear, you should be thinking lines. So this is an equation in sine theta that's linear. So we could say this equation is linear in sine theta. So that's why it's called linear. The process of solving is identical to what we did before. But in this case, we're restricting ourselves to 0 to 2 pi. So we won't need to consider the repetitions in this example. We will in another example, but for now, we're not going to consider repetitions. But the process of solving for it is the same. You just want to solve for theta, so move everything away from theta that you can, and then think about the arc sine, or really just think about what angles give you a sine of that value. Here we go. So if you solve this for sine theta, you get this. So what we're looking for is we are looking for angles where the sine is negative root 3 over 2. So how do we do it? We imagine the unit circle. Let's see, sine is negative root 3 over 2. Okay, that's going to be down here. This is negative root 3 over 2. But then this is also, right? So negative root 3 over, negative root 3 over 2, negative root 3 over 2. What are the two angles? Well, you've got 4 pi over 3, which is the first one here, and then you've got 5 pi over 3, which is the second one. 5 pi over 3. There we go. Now, I had this cautionary note at the bottom, and this is one of the reasons why when you're working with inverse functions, you have to be very careful and think about domains and ranges. If you were to actually use sine inverse to solve this, meaning if you go back to this step and you take the inverse sine of both sides, you'll actually get the wrong answer. And that's because, remember, we specifically restricted the domain of the sine function to talk about invertibility. So, for example, if you plug this into your calculator and you do arc sine of negative root 3 over 2, it'll give you the answer negative pi over 3. But that's not the answer to the question. The question says that our angle needs to be within the interval 0 to 2 pi. So negative pi over 3 is not in that interval. So in some senses, it's kind of treacherous to use the arc sine function or to use the arc functions, especially if you're using a calculator. So long story short, beware when you try to employ arc sine and arc cosine and arc tangent and stuff, because the domains were restricted then, and the domains may not be restricted in the correct way for the question that we are trying to answer. All right? Okay. Let's try this one. So here we've actually got a trigonometric equation in quadratic form. So what I want you to do for a minute is look at this and think about how you could structure it, or think about how you could look at it as if it were just a quadratic equation. All right, now let's do it together. Basically, this here is sine squared, and this is sine. So if we were to call sine of theta its own letter, I think I use y. Do I use y or u? Oh, I use u. So think about it like this. If we said, let u equal sine of theta, then our equation becomes 2u squared minus 3u plus 1 equals 0. And that's just a standard quadratic equation, right? So you probably spent a significant amount of time solving things like this in high school, in the past, in a pre-calc class, if you took that, in a college algebra class or an intermediate algebra class. It's just a quadratic equation. So you can solve it using whatever methods you prefer. There are three ways to do it. You can either factor it, complete the square, or quadratic formula. In this case, I think it factors nicely. So let's go to the next slide. Yeah, a quadratic expression in sine theta. So this one actually does factor. So if you think about this quadratic equation, it's equal to that. But remember, we let u be sine of theta. So if we substitute sine theta back in for u, then this is what we get. There we go. So we can factor that equation using the same techniques that you've seen in the past. One note that I'll add here, because students will usually ask me, you don't need to do this substitution. You don't need to do this substitution for a letter u if you can just see how to factor it outright. But when you want to make that step is really up to you. For example, like I've been working with equations like this for so long that right away I could jump straight from here to here. But if you're not comfortable with that step, that is totally fine. And I strongly recommend that you do this substitution first and then go through these intermediate steps. And then if you do that many times, eventually you'll reach a point where you're like, I'm not even going to bother writing u anymore, because you'll be able to see that you can treat sine of theta as its own object. Sine of theta is just an object. So you can move it around algebraically like it's its own object. All right. Now, if we set this result here equal to 0, then we get two possible solutions. We'll get sine of theta equals 1/2, sine of theta equals 1. All right, so what are some angles that'll do that? Well, let's think about the unit circle again. It's always that unit circle, right? It's always going back to the unit circle. Imagine the unit circle, draw the unit circle, think about the unit circle. Here we go. So sine of theta is 1/2. Sine is vertical displacement, so we need the displacement to be 1/2. We're looking at this and this. So this first angle here is going to be pi over 6, and then the second angle here is going to be 5 pi over 6. All right, so there's two solutions already. And then what about sine of theta equals 1? Okay, so if sine of theta is 1, that means the vertical displacement is 1, and so that angle is going to be pi over 2. All right, so we've got three solutions. We've got pi over 6, 5 pi over 6, and pi over 2, just like so. All right. However, notice that we weren't given any restriction on where these solutions need to lie. They can lie anywhere in the domain of the sine function, which is all real numbers. So once you get these particular solutions that lie in the interval 0 to 2 pi, you then need to add 2k pi to consider the repetitions, the periodicity. So that's what you do. Add 2k pi to each of your particular solutions, and then you get the general solutions. Voila. So there's infinitely many, but they do have, I should say, there are three solutions in every 2 pi interval. And let's actually take a look at the graph. We haven't seen a graph of anything like this before. So let's check it out and we'll see how those solutions appear. So here's what I've got. I graphed 2 sine theta minus sine theta plus 1, or 3 sine theta plus 1. And I marked the solutions here. So here's the three solutions we found. This one was, what, pi over 6. This one's pi over 2. And this one's 5 pi over 6. So there are three solutions in the interval 0 to 2 pi. which is, let's see, 0 to 2 pi is about here. There's the three solutions, 1, 2, 3. But then when you add 2 pi to each one of those solutions, you get another solution. Add 2 pi, add 2 pi, add 2 pi. And there's three more solutions. Then when you add 4 pi to those original solutions, you'll get three more. And if you subtract 2 pi, you'll get three more, and it keeps going and going and going because the domain is all real numbers. That's why we needed these. There we go. All right, next, let's talk about how to solve equations like this using identities. Oh, and I forgot to put a pause here. So pretend you can't see this for a minute. Ignore this, pretend you can't see it for just a minute, and think about how you would solve this equation, and maybe even try something on your own. I'll throw up the emojis here. All right, now let's do it together. So one thing you should notice is that this equation has both sines and cosines in it. Sines and cosines in it. And what you'll find is if you try to mess around with it and try to solve for like cosine theta, or if you try to solve for sine theta, you can't really get to theta in quite the right way. Like you can't extract things enough to get to theta. So one thing that really helps is to use one of the identities that we've learned. We're actually going to learn many, many more identities. That's the next several sections is just like dozens of identities, but we'll talk about that next time. So the one that we're going to use for this equation is the Pythagorean identity. This is one of the identities that you should have memorized. You do need to memorize it. Memorize this identity. You must have it memorized. Just I want to emphasize that. But if we take this identity and we rewrite it like so, if we solve for sine squared theta, we can then substitute sine squared theta with 1 minus cosine squared theta. And when we do that, we'll now only have one type of trigonometric function. So here we go. Replace sine squared theta with 1 minus cosine squared theta. And now in this equation, we only have cosines, which could be handy because maybe we'll get this in, maybe this will become a quadratic equation in cosine, or maybe it'll become a linear equation in cosine, or maybe it'll become a cubic equation in cosine. And we can solve it using other techniques that we have. That's exactly what we're going to do now. So in this case, we will end up with a quadratic equation in cosine, right? 2 something squared plus 3 something plus 1. Thankfully, this one factors. And then using the zero product principle, we get that 2 cosine theta plus 1 is 0, or cosine theta plus 1 is 0, right? So you set each of these equal to 0, equal to 0, equal to 0. And then when you solve those for theta, you'll get that cosine theta is, you'll get that cosine theta is negative 1/2, or that cosine theta is negative 1. All right. Then you imagine the unit circle again. You imagine the unit circle and you say, what angles give us a cosine of negative 1/2? Let's see if we can do it together for a minute here. All right, if cosine is negative 1/2, that's the displacement. So that means the displacement is going to be negative 1/2. So we'll have something like this, or like this, right? So we've got this angle, which is going to be, what is it? If it's 1/2, that's the short leg, so 2 pi over 3. Then you've got this angle here, which is 4 pi over 3. Yes, there we go. 2 pi over 3 and 4 pi over 3. Then for this equation, what angle has a cosine of negative 1? Well, let's see. Cosine's horizontal displacement. So if the horizontal displacement is negative 1, then that means the angle has to be pi. There we go. Now, notice in this problem, we are actually restricted. So we found the answer. It's those three solutions, and those are the only solutions in that interval from 0 to 2 pi. If we didn't have that restriction, we'd have to consider the repetitions. We'd have to add 2k pi, and so on and so on. All right, now lastly, Let's talk briefly about solving these trig equations using a calculator. I don't have a specific example for this one because the examples are really quite plain and trivial. Essentially, if you want to use a calculator to solve these, you use the inverse trig functions. So if you look on your calculator, you will see, usually it's, I don't have mine here with me. Usually it's right above the trig buttons. So you'll have like sine, cosine, tangent, and right above them you should have sine inverse, cosine inverse, tangent inverse. So if you need to solve an equation like these ones using your calculator, you're just going to take the inverse trig function. So for example, if we got to this point, let me erase some stuff. Let me erase some stuff. If we got to this point, and let's say we didn't know what theta was going to be. Maybe we were given a value that doesn't correspond to standard angles. In that event, you can go to your calculator and you can basically say cosine inverse of negative 1/2, and it will give you, see, it will give you an approximation. It'll give you an approximate value of that number. And that's how you use a calculator. But be wary. Be wary for two reasons. One, make sure your calculator is in radian mode, because sometimes it's not. But even more importantly, I would say, remember the restricted domains used to define the inverse trig functions. Your calculator has those restrictions built in. And so it may give you incorrect results, just like in example 6 before. Um, it's a calculator. It's not smart. It doesn't know what you're trying to do. All it knows is how to calculate. So if you have it evaluate cosine of negative 1/2, it's going to consider the restrictions that we defined in the previous lecture, the one 6.1. But that's pretty much it. So you can use a calculator. Just be wary that it's in the right mode and be wary of the domain restrictions because it may give you the wrong result. All right. So that's it for this section. Once again, thanks for bearing with it. I know it's a little bit long. It's a lot of content. You should go start the homework, try it on your own. And next time we are going to talk about, I forget which identities it is, but I'll say this. The next several sections are just learning a catalog of identities. Geez, I mean, I'm pretty sure there's like 36 of these identities. One thing I'll say is I do not require you to memorize all of those identities. Some professors do, but in my experience, there's only about 6 of them that you should absolutely have memorized, and I will be very clear about which ones those are. The other ones, if you remember them, great. If you don't, you'll be fine. On the test, I will actually just give you the list of the ones that you don't need to memorize, but I will not give you the ones that you should have memorized. In fact, I will say on there, you should have this one memorized. Um, but we'll get to that next time, so I'll stop rambling. Thanks again, everybody, and I will see you next time.